Boa tarde a todos. Bem-vindos a mais um seminário do Departamento de Geofísica. Só para avisar, hoje é o nosso último seminário desse ano. Então, antes de começar, eu queria agradecer algumas pessoas envolvidas nesse trabalho, né? A gente conseguiu continuar com a programação dos seminários, mesmo sendo online. Então, eu queria agradecer a Elisa, a Luana, da Secretaria, por todo o apoio que elas deram. O Richard, por todo o apoio na parte de mídia, do YouTube, as reuniões no Google Meet, e os meus colegas da organização, o Ricardo, o Felipe e o Jaime. Então, obrigado a todos por acompanhar a gente até aqui. E hoje a gente vai ter uma apresentação do Sina Saneiyan, que é iraniano. Então, eu vou apresentá-lo em inglês. Well, on today's seminar, we have Sina Saneiyan. He has a bachelor's degree in mine engineering from the University of Tehran. Then he continued his studies and got his master's degree in petroleum engineering at the Sharud University of Technology. Then he got his PhD in environmental science at Rutgers University, where he is now a postdoctoral researcher. Sina will talk about a code has been developing for modeling and inversion of electrical resistivity and induced polarization. So thank you, Sina, for accepting our invitation. And now I will hand over the presentation to you.
You're welcome. Okay, let me just. Oh my God. Thank you for the introduction and the invitation. I'm glad to be presenting to your department. About 2 years ago, a few friends of mine, including Guillaume Blanchy, Jimmy Boyd, and Paul McLachlan, and Professor Binley, decided to provide the students and the geophysicists who are working in the field of geoelectrical measurements with a software that is easy to use and at the same time complex enough for analyzing their data and doing modeling in geophysical geoelectrical domain. And for that, Dr. Binley already had very powerful codes that he written in Fortran, where they were capable of doing inversion and modeling of complex geoelectrical measurements, as well as ERT in 2D and 3D. But the problem with those codes and most of these freely available codes was that they require a complex input file and they have a steep learning curve. So we decided to completely eliminate that complexity with a software that, even if you don't have enough knowledge of any of these complex input files or even the geoelectrical measurements for themselves, you would be still able to conduct your analysis. So before I start to talk about what I'm doing, I'm going to introduce you with the general coding workflow that we decided to use for ResIPy, as well as the whole software's workflow, and a few explanation of what actually GUI does. So this graphical user interface does. And then we're going to see some data processing, including importing data, what formats ResIPy accepts, how you can filter and clean your data, as well as some error modeling capabilities that ResIPy is capable of doing. And then I'm going to discuss the one of the most powerful elements of the software, which is definition of the finite element mesh and forward modeling. Inversion is something that many of people have done, but forward modeling usually requires a bit of, you have to create your model, and creation of the model usually requires a lot of complex input files. But with ResIPy, in both 2D and 3D spaces, you're capable of doing this with a few clicks of your mouse. So we decided to use Python 3 language for coding of this software because Python is very powerful and is very globalized, and everybody kind of knows what Python is capable of. And whenever we had a problem, we didn't understand something, or we wanted to do something with a simple Google search, you could have just find something similar and basically improve your coding. That's why we chose Python. And Python is an open source coding environment, and that doesn't require purchasing a license like MATLAB or anything like that. And that's why we chose this programming language. Our code is an object-oriented workflow. meaning that we are using something called classes, and this provides you with the opportunity to define an object that includes all of the capability of ResIPy in one programming object. That means you don't have to, if you're an environment that you can code rather than just using the graphical user interface, you don't really need to open and close your programming interface to do different data analysis with one programming interface. That's what the object-oriented workflow will bring the programmers. Additionally, with choosing this path, we were able to separate the programming interface from the graphical user interface. This means that the actual engine behind this GUI that we are seeing is completely separate from the GUI itself. It's going to provide all the people who can code with the ability to change the main engine, but not to interfere with the GUI. And they can add their own features if they like. We can change it while the GUI is working fine. This provides the additional opportunity for people who want to learn programming in the geophysical community. You can use the API without the GUI and still learn about coding and doing your data analysis in the complex environment of programming language, rather than just using the graphical user interface. The general workflow that ResIPy follows is very straightforward. ResIPy is capable of doing an inverse problem, solve an inverse problem, and also do a forward modeling. So what is an inverse problem? Basically, in your inverse problem, you have some data that you have collected from subsurface with a general electrical resistivity or induced polarization array from the surface, and you want to create a subsurface model. For that, you will need to import your data. You need to filter the bad data points. And if you have some other type of measurements, you can additionally do error analysis with ResIPy. And after that, you have to define a finite element mesh, meaning you have to discretize your subsurface into tiny bits and try to change each tiny bits to receive a whole picture of the subsurface. These are all conducted through this inverse problem that is happening inside ResIPy's engines called R2 or CR2 or R3T and CR3T. The other way is when you have a hypothesis, when you know that, okay, I have a subsurface that will look like this. For example, there is a tank that is buried in subsurface, but I want to see if I take out an array and an instrument, what will the data look like? For that, you will need to do a forward problem. Basically, you turn your hypothesis into actual data points. So basically, you are supposed to build an array, and then on that finite element mesh, instead of changing them to get the model, now you assign values to that finite element mesh, and then you can add some errors to it to make sure it's more realistic, like some percentage of noise, and then get the data. So this is forward model. Both of them in 2D and 3D are possible with ResIPy. The good thing is that you do not need any special input format files, although ResIPy already accepts a lot of different input format files. But if you don't have that, you are okay. All you need is just different columns of data and just import them in ResIPy and do your data analysis. Additionally, you definitely don't need any external processing. You don't need to clean up your data before importing them into ResIPy. This makes ResIPy a very simple yet intuitive software that has everything all in one package: plotting, data analysis, filtering, and even post-processing that we are going to discuss in a non-linear workflow, which is meaning that you don't really need to step by step do something to get your data or model. You only need to follow a few of them. Or if you want to do a very thorough data analysis, you can follow all the steps available. But to put it in perspective, all you need to, for inversion, for example, you need to import your data and click on the inversion. And all the way, you get your inversion with default parameters. That usually turns out a good result. But sometimes, if the subsurface structure is more complex, you need to tweak some parameters. For example, in here, you're seeing that there is a, there we go. For example, in here, you're seeing that we have a 3D pseudo section that when we can assign a final element mesh to it and then simply invert it, and by assigning different values to for isosurfaces, we can just simply say, okay, maybe this orange one is contamination in subsurface, and so on. So importing the data, you are capable of importing with file formats of famous softwares like Res2dinv and Res3dinv, as well as some not really known codes, but very powerful ones like PyGimli's BERT format or E4D format. These are the specific file formats that you can import. And if your topography information are already included in your importing file, such as this one, you will get a beautiful pseudo section of the measurements. If you have IPdata, also you can check induced polarization, or if ResIPy already understands this, that there are IPdata available if you're choosing one of these standard file formats, also that will be checked automatically. And then right away you can invert your data. Now, some of you might say, okay, we don't have any standard data formats, so what are we supposed to do? Do we have to change the input file? No, of course not. All you need to do is just import them and select the columns related to your electrodes and resistivity or resistance values and import them in ResIPy. And then you can go into the topography tab and simply add your electrode locations, X, Y, Z values. And if they are buried in subsurface, you also can check that. And then import everything and start your data analysis. And it's also important to note that sometimes you don't have the actual topography values for every electrode you have. And for that, all you need is just a few data points, and then the rest can be interpolated linearly if they are missing, like this one, for example, if we interpolate that linearly and you are good to go. Additionally, sometimes you have a surface that is more complex than just a few electrodes that you laid down on it, and maybe the electrodes are pretty sparse. In that case, for that specific topography, you can add additional topography points, meaning that if your electrodes are around a mountain, but you need to see the inside the mountain, how it looks, and or the topography structure of the mountain should be included. So you can actually add that as well. If your data includes some reciprocal measurements, meaning that your data has the current electrodes as at position 1 and 2, and the potentials at position 3 and 4, and then you just swap them, then now potentials become at the locations 1 and 2, and currents go at 3 and 4. Then in theory, the measurements are supposed to be from one point in subsurface, and they should be exactly the same. But in practice and reality, this is not the case. There is human error, instrument error, even electrode location errors, and so on. So that may not be the case. If the specific measurement doesn't look good, you have to either clean it up from your data, or you must assign a weight to it to make sure that it does not affect your overall data analysis and inversion significantly. For that, you can use the filtering capabilities in ResIPy. The simplest of the filtering is basically clicking on, for example, a bad electrode and remove it, or clicking on individual points on the map and remove it. And also you can remove whatever percentage of the reciprocal error you like from your data set. Additionally, some instruments provide dummy measurements. One of them is Syscal, Iris instrument Syscal, so you can also remove that as well. If your data includes phase values or IP measurements, since IP data is far less, the signal to noise ratio is smaller than the actual resistivity, you need more filtering capabilities. Resistivity provides you with a lot of filtering capability, including range filtering, meaning that if you think you're working in a near surface environment, and for that you may not expect to see high values of phase or chargeability, you can filter them out. If your data include individual decay curves for the chargeability measurements, you can also use something we call a DCA, or decay curve analysis filtering, which basically creates a master decay curve, and based on that master decay curve, we'll compare all the individual decay curves, and if certain of those measurements are outside of a certain standard deviation, those data points will be filtered out. Additionally, it has been shown that the chargeability and phase shift at low frequency measurements have a linear relationship, and therefore you can interchangeably use them in your data analysis. We provide you with a conversion capability that you can simply change chargeability values to phase shift based on the instrument that you're using. It is important to note that all the filterings, you can reset them and go back if you don't like it. If too many data points have been filtered out, you can just reset everything and start filtering from the beginning. Now, if your data includes the reciprocal measurements, you have the possibility of doing some error modeling. The benefit of error modeling is that you assign some weight to the points that you're measuring, and this weight will act as a restriction for the effect of that specific point in your overall inversion. Meaning that if the reciprocal and the normal did not match perfectly, and simply they are not a good sort of a measurement, you can assign a low weight to them, and that ensures that they are not affecting your inversion too much. And if certain data points have a good quality, meaning that their normal and reciprocal pair are pretty similar, you can assign a higher weight to them and make sure that actually affect your inversion better than the bad quality data. You can do the error modeling for both resistance and phase, if available phase, and you're provided with linear and parallel for resistance, and parallel and parabola for the phase shift values. But it's important to note that you're not just bound to this linear or parallel. You can add your own method to the API if you like. If you know Python programming, it's very easy to just simply follow these steps and create your own function, and then you will have different, for example, I don't know, second degree polynomial or something like that to your resistance if you like. And the last step prior to inversion is creating your finite element mesh. In 2D and 3D space, this is provided for simple surface and borehole measurements, across borehole measurements. For example, in this specific mesh that you're seeing in here is a surface study. If your model is more complex than this and includes a different type of, if it's a closed boundary, for example, or if it's something that not as simple as a surface measurement, you can simply import your mesh, your custom mesh, and use that. And you're not bound to just whatever ResIPy provides to you. Additionally, you can control the depth that you want to investigate yourself. You can control how these elements are getting enlarged with depth and so on. And you also can assign some known anomalies or values to your mesh as well. For example, if you have a river and you know that river does not need inversion because its resistivity is already known, so you simply assign, create the river and simply assign a value to it and fix that region and make sure that it is not affecting your inversion. Now, I want to show you how ResIPy works in action. So for that, I will show you two simple modeling for 2D and 3D 4 modeling. And if time allows, I'm going to show you a cross borehole inversion. For that, if you're using a computer, you can simply download it now from our GitLab repository, or scan this code and it directs you to the download page. And then we can just we can both work with it at the same time. But if not, let me just start with using ResIPy. If I find it, where was it? Sorry. Okay. So if you're a developer, you can also download the source code like what we have in here and run it through the source code. But if you're not, compiled packages as single executable files are also provided that you can simply use those. I hope the quality is good enough that you can see something, but let me know if it's not. All right. So for 2D, just to confirm, you're seeing the software right now, right? Okay, good. Great. All right. So for 2D for modeling, you're selecting 2D and then checking forward. By default, it's always on inversion. And then if you have in your hypothesis, if you have induced polarization data, you're going to check that as well. This example is going to be very simple. So I'm going to go with like 24 electrodes, 1 meter spacing, and just generate an array. Okay, so you have the electrode labels and also their position on the ground. You also can give it topography if you have. And then there are few options like making a quadrilateral mesh. I don't really like it. A lot of people don't like quadrilateral mesh, but we're providing the opportunity. The thing is with quadrilateral meshes, usually you can have complex topography because these are blocks and then your topography will look like a block kind of situation. So for that, it's better to always use the triangular mesh. Triangular mesh is much easier to work with and usually runs faster because the cell sizes increase with depth better than the quadrilateral mesh. You also can design your model prior to meshing and only available for triangular mesh, which I'm going to do right now. The benefit of this is that, for example, you know the subsurface structure's shape. For example, if you have a tank, right, usually is rectangular, right? So I'm going to add a rectangle. And then I'm going to create my mesh, and my anomaly looks exactly as a rectangle. The other thing is that you have to assign a value to it. I'm going to make a conductive feature, which is about 20 ohmmeters, and also some degree of polarizability to it, like 20 milliradian. Okay, and then you go to the forward model tab. In the forward model, you are provided with standard array formats like dipole, Wenner, and so on. Additionally, if for some people who don't know how they might look like on the ground, we provide a simple graph that shows, okay, what this A or N means. For dipole, this factor A basically is a factor multiplied by your electrode spacing, and N is the number of skips, meaning that when these M and M gonna go with 1 skip and then 2 skip and so on, and eventually 8 skips. And then when this one is reached, we move A and B 1 ahead. You also can add noise to your data to make it more realistic. So I'm going to add like 3% noise to resistivity and also 1 milliradian noise for my face. And then you can simply run forward model. As you can see on the pseudo sections, you're clearly seeing this conductive feature that is also polarizable. You can counter this if you like to see it better. And if your screen is small, you also can just drag this up. So these are plotting features available. If you're doing inversion, right away after the forward modeling, you don't need to change any of these guys that are inversion settings. But in case you're doing an inversion, you're provided with detailed explanation of what parameter actually can be changed in the actual engine of the inversion with a detailed help. And sometimes you need to change these guys to get a better result. For that, it's always good to click on them and understand which one means what. And then I'm going to run this inversion. Depending on the computer, it usually runs fast, but sometimes can run slow. Okay, that was pretty fast. I just wanted to explain that you also get the reduction in RMS versus the iterations. It is always good to know that when you're doing any inversions, that the value of RMS should be reducing with iterations. If it's not that the case, you have to go back and usually change some inversion settings or add an error model if you can, or change some of these default error values that we have in here, and then go back, and usually that helps a lot. All right, when we go to the results tab, you will be able to see, for example, right now you have a forward model. You can see your initial model, and you can also see its inversion results. You can see different parameters that the inversion outputs, for example, magnitude in ohmmeter. And as you can see, we assigned 20 ohmmeters, and it's clearly this area in here. And phase, for example, again, minus 20. This is the region with the high phase value, and so on. There are a lot of features you can use, conductivity and so many things. But sometimes the value you're looking for is not in here. For that, you can go to compute attribute and simply from this parameters in here, calculate the attribute you're looking for. For example, you may want to calculate the moisture content. And we know that we can change with some information from the subsurface, we can calculate that based on resistivity. So you simply can use the resistivity in here and calculate moisture content and get the moisture content plot in here. You also have the ability to use the depth of investigation. DOI in here stands for depth of investigation. ResIPy has two approaches for that. One is just an estimate based on the sensitivity of your array and measurements. As you can see, since this part is more conductive, the depth of investigation is shallower. You also have the actual a better approach, which is we're calling it model DOI, is based on a well-known method introduced by Oldenburg and Lee in 1999. Basically, we invert your data 3 times, with twice of those times being restricted to the background from the background inversion, and one just as regular. And based on comparison between these two, we will get a more accurate depth of investigation. If you really want to know about that, I can give you this reference for more information. And at the end, you will have the ability of doing post-processing. Post-processing is basically just checking how the inversion errors are looking. And sometimes you may have a bad inversion, meaning that the normalized error, which is supposed to be between -3 to 3%, it's not, and it's far more than that. And for that, you can either go back and change some inversion settings and redo it, but sometimes there are some few data points that you can't just clean up like that. So for that, you can simply either remove them from the pseudo section like that, or you can just select keep whatever is between -3 and 3, or whatever that's more acceptable for you, and just clean up those bad inverted results. But for this specific inversion, everything went just fine. And always refer to the help of the software. We have a very simple general help in here that gives you an idea of what each tab does and how you can export your data and use them in third-party apps such as ParaView for better visualization, or where your data in XYZ format are stored, and so on. Additionally, we provide a detailed documentation of what each of these functions do. And additional to that, we have video tutorials on YouTube that you can just simply watch for more complex examples than what I'm trying to show you today. If you're more into inversion, definitely read the README files of the inversion and modeling engines used in ResIPy, R2, CR2, and so on. That will give you a very good idea of what's going on in ResIPy. Now let's do a 3D forward modeling. For that, I'm just going to restart everything and then select 3D and forward. Similar to 2D, you have to define your electrode array. I'm going to use 12 electrode. Now in 3D, it is per number of lines you have. So it's going to be 12 electrodes per line. I'm going to have 4 lines and 3 meters of spacing and 2 meters of spacing between electrodes, and generate. As you can see, the X locations are apart with 2 meters of spacing, and then Y locations of electrodes is 3 meters. And again, if I go to Mesh tab, now you don't have the capability of doing quadrilateral or triangular anymore, but you have the tetrahedron mesh. It's the 3D form of like triangular mesh. And you can create your mesh. Now on this one, you have to select your anomaly. You don't have the capability of designing your model anymore, because it's pretty hard to code something that works on undefined space, let's say. So for now, the only possibility is just to select the points that your anomaly would be ideally. You also have the capability of changing the element size and everything. If you hover your mouse over any of the parameters in any part of ResIPy, you will get a short help, which what that specific tool does. For example, characteristic length. That means that is the length of each element. For default is 2 elements per 2 electrodes, or 1 node per 2 electrodes, and so on. Okay, for modeling 3D, you have to first define your anomaly region, which simply okay, I have some issue again. All right, I just realized the bug. Okay, I'm gonna do it like that. Okay. All right, so you have to define your selection box. All right, so the selection box will be like that, and you can move it to. For some reason, it's not working as I expected, unfortunately. Oh, there you go. Okay, it's again, it's in 3D space. It's not so easy to select these parts, and sometimes it's hard to get the handles perfectly. Anyway, so this box will act as a selection for the elements on the mesh. So now you have to add the region, and it automatically will select all the elements available in the mesh that are inside the box. And sometimes it's not perfect because you also selected something a bit outside, and that's going to get selected. So forgive us. This is just some rudimentary modeling approach. But anyway, we can give it a 20 ohm meter, again, more conductive. You're also available, again, you can use any of these, a standard one, but sometimes as you're using I forgot something very important. You have to use exit mode, because if you don't use that, then you're not having any selection. All right, so there's 2 zones here, this one, 2 regions actually, and the background region and the conductive region, right? Now, we defined 4 lines, and there were these, right? But in 3D format, you can have any number of any combination you like, any 4 electrode combination you like. For that, it's always good practice to use the custom sequence importation. You basically define your electrode locations on the grid and import them in a 4-column data format. But if you don't want to do that, you can simply use any of these dipole, Wenner, or something, and ResIPy automatically figures out the lines. As you can see here, it kind of figured, okay, this is 1 line, this is 2 and 3 and 4. But your actual grid might be just exactly opposite. So for that, you have to use the custom sequence. Anyway, so you have this 3D sort of pseudo section, and you can see the conductive part in here and the background. And similar to the 2D inversion, you can simply go and invert this. And as you can see, you can either look at it as like a block like this, or you also can have the grid, or you can do much more with it. You can slice this. Okay, I'm going to slice it at y equal to 8, and also a few slices at different x locations, maybe one at like 15, and then one at 10 and one at 5, and also Z at -4. Okay. And then you have this slice. You can slice through it and see the inside of the inverted block. Additionally, you can change the color map and look at it. And you also have the capability of selecting what part to be shown. All right. So for example, I don't want anything to be shown above 30 ohm meters, and I can select that. Oh, sorry, this is in. Okay, I have to figure this. There we go. 30. Apply. Okay. So now anything above 30 is excluded from the plot. Also, you can use the isosurface similar to that. If I choose 30 and apply that, it will only show the surface of the feature that had 30 ohm meter and nothing inside of it. You can separate these values by comma. And if I select like 90 in here, 30 and 90, and apply that, you also see the 90 in here. And also post-processing again, always look at this. If your inversion went not good, go back and change different parameters. All right, let's go back. All right. Okay, so I prepared a few videos that no longer required because I showed you the software. And because of the time, I'm not showing the cross borehole either. It's very simple. The examples are available and on our repository as well as the YouTube channel. But let's see actually what ResIPy is capable of doing. Let's look at some case studies. So with electrical resistivity, we can kind of identify different type of plants, genotypes of plants, because of the way they uptake moisture or water from the surface to as the source of their nutrition pathways. In here, Wally et al. In 2017 went to a field that was planted with wheat, and they started to do some ERT monitoring over time in 3 different months. And based on the differences that root water uptake showed on the ERT result, they figured out what's going to happen if different type of wheats were planted in that area. For that, they conducted a time-lapse ERT survey. Basically, a time-lapse ERT survey is when you measure the background, meaning the actual survey area, and then in future times you come, do the measurement, but now just invert the data based on the changes you're seeing. That's why, for example, March is in here, shows no % changes that much, around 0, because it's very close to the background, which was in April. But as you go, you can see more resistive features are appearing at the surface, indicating that the wheat plants actually uptook the water, and that's why the surfaces get drier and drier. So this is one thing that you can do with ResIPy. Simply go collect your data and come back and feed ResIPy with your data and do a time-lapse inversion and see how it looks. No longer required to do any different type of coding or making different meshes or anything. Everything is done automatically. Another case study is done in a riverbed to understand the interactions between the groundwater and surface water. It's very important to know these interactions and also to know the subsurface structure underneath a river. For example, if a contamination is in the river and how it's going to get into the groundwater, which is the source of drinking water for most of us, or agricultural activities, it's very good to know if there is a pathway for that contamination to get into the groundwater. That's why it's always good to know these structures under a river. For that, a few people led by Paul went and laid down their electrodes underneath a shallow river. and conducted a few ERT measurements. But now they had to include the river in their inversion because they knew its resistivity and they didn't want the inversion to include that. ResIPy provided them with the opportunity to create a complex topography, include the river, and bury the electrodes under the river and fix the river and do an inversion. And with that, they realized there is a resistive gravel part underneath the river with a much more conductive peat structure at the river bank. Another case study that ResIPy can help is studying landslides. There is a landslide observatory in United Kingdom called in Holland Hill region in Yorkshire, which has been under different type of monitoring since a decade ago, I think. And people are doing that to kind of predict landslides with the moisture contents and moisture dynamic changes over the years. For instance, in a study conducted in 2015 and through 2016, they realized there is a resistive structure which is topped with a conductive structure. And with more geological studies, they saw that this part is mudstone and this is sandstone. And when the moisture content increases inside this muddy area, it usually starts to flow over the sandstone. With a time-lapse analysis during that year, starting from July, they realized the surface, especially around this muddy area, is getting drier and drier. And eventually, because of some rain and precipitation that happened in the area, the landslide occurred, and post-measurement, electrical resistivity measurement showed that this area has significantly lower resistivity compared to previous times, meaning that it actually got more wet. So if they had higher resolution, temporarily higher resolution measurements, they could have kind of predicted that, because if the resistivity decreasing and it's getting more wet, you can kind of assume, all right, this mudstone is going to slide sometime soon. They also conducted that in a 3D survey. They laid down a grid like that over the area of about 100 meters by, I think, around 30 meters or something. And in 2017, and they clearly identified the mudstone flow lobe, that the rupture would happen from here and then kind of flow over the sandstone. But over the time in 2017, the difference resistivity inversion showed that actually the whole surface is dry, and there is no indication of a more wetting area top compared to bottom. So probably landslides possibility is not really a thing anymore, at least not now. So with that, I'd like to thank you. We try to make ResIPy accessible to everyone, especially for those in education, because we know the cost of commercial software, like Res2the, for example, they are pretty expensive. We chose it as an open source software because we like your feedback, we like you to contribute, we like everybody to edit the code and add good features to it. For example, a few weeks ago, a friend of mine told me that I added a feature that you can convert the local grid to UTM grid. Do you like it? And I said, of course, please give it to us. We will tweak it and make it work with ResIPy. So in future, you would also be available with conversion from local grid to UTM grid. And at the end, why not open source? Everybody likes free stuff, right? And with that, please help. Please try to contribute, and go visit our repository or watch our YouTube channel. Additionally, you can follow our ResearchGate page. In that, we are showing you the updates that happen over time, and you can follow the updates. Thank you very much.
Thank you, Sina, for your presentation. The software seems to be very easy and intuitive to use, so it might be a great add to people who use the method. So I'm going to open our session to questions so we can talk a little bit.
Okay.
And whoever is here in the Google Meet can talk directly. And I also see if there are questions in the YouTube channel.
Okay.
So there's a question on YouTube. Marco Antonio is asking, first, thanks for the presentation and asks, does ResIPy invert resistivity and IP jointly?
Yes, it does invert them at the same time in a complex conductivity format with CR2. So what it does basically converts the chargeability if you have, or if the phase shift is provided, it's just going to use that directly, and then make the complex conductivity and then invert on that. So it kind of jointly invert P, I guess. Yep.
Thank you.
Okay, it's from Pedro.
Yes,
It
he's
says,
asking.
I have a curiosity how ResIPy interpolates missing points linearly. So in 2D or 3D space doesn't matter. It's just linearly. If you have one point at top and one point at bottom, there is a line, and just choose on that lines, or diagonally, whatever. It's all going to be linearly.
Thank you, Sina. There are other questions on YouTube. Leonidas asks, ResIPy accepts only the lines that have the same number of electrodes to perform the parallel 3D inversion, right?
Can you repeat the question again?
ResIPy accepts only the lines that have the same number of electrodes to perform the parallel 3D inversion, right?
I'm not. It was before like that. I'm not sure anymore. We tweaked it a lot. I have to check, but might be the case. I think one person had this issue before. We addressed that. I think you can include different lengths of lines or number of electrodes. I'm not sure anymore, but I have to check. But I think if you have the right grid for yourself, you can try it and see if that's the case. Yeah.
Okay, he also asks, if the lines have different numbers of electrodes, is there any way to enter the data and generate the mesh?
Yeah, the mesh generation is different than the number of electrodes or their length. It just simply uses the whole area that the electrodes are available. And based on that, the electrode is going to be put on the mesh, on the nodes closest possible to the nodes on the topography or the grid, right? If your electrode is at X, Y, Z, all 0, and then you have a mesh node that is at 0.1, 0.1, 0.1, the electrode is going to go on that, for example.
Okay,
so it's
you.
completely separate from your grid, I would say.
And Juliana has a question about the topography. How can I input the electrodes coordinates, like Z69 datum and elevation?
So ResIPy works with a local grid right now. So if you have UTM data, you have to change them to local grid. And also for topography, it's just meters for electrodes, right? If their height above the sea level, you can put whatever you like. Yeah.
Okay, thank you.
Cool.
There's another question from Pepe. ResIPy works with any array, conventional or unconventional?
Yes, anything. Pole, dipole, mixed array, conventional or non-conventional. It doesn't really matter. As long as you have the exact position of the electrode and their locations on the grid, you're good to go.
Okay, thank you, Sina.
You're welcome.
Any other questions?
I have a question, Sina. Would you be able to, for example, if you have a bunch of 2D lines that you inverted from a site, but you don't want to do a 3D inversion because they are not parallel, or maybe they are a little bit sparse, but it would be helpful to see them in a 3D perspective. So would you be able to just display these lines as you showed in your 3D inversion? You know, those like crossing lines?
Not directly in ResIPy. You can't do that. No. You have to. You can use ParaView for that, which is very easy to do. But
Okay.
that actually is one thing that that friend of mine who changed the UTM to the local grid to UTM was looking after, and for right now you can't just put 2D lines with each other and make a
Just for a
pseudo
display.
3D.
Okay.
Yeah.
Okay.
Pseudo 3D is not possible now.
All right.
Thank you, Sina. Does anyone has other questions?
I have another one.
Go ahead.
Because we have been using ResIPy for in our classes, me and Carlos Mendonça and our students, and we were a little bit we would like some advice for how to use the like smoothing parameters. We were not very it was not very clear to us how we could change those parameters in the inversion settings. So
like
would you
L2,
say
L1 kind of things?
Sorry?
You mean like L2 inversion or L1 inversion?
Yes, exactly. Yeah.
Yeah, so unfortunately, the Dr. Bentley is not a fan of the robust or L2 or L1. Which one is that? The non-smooth one. So
The
at the
robust
moment,
one? Oh, okay.
yeah, so we don't have the capability of doing a non-smooth inversion at
Oh,
all. So you
okay.
can't change that. Yeah.
All right.
We asked him to include it, and he was like, it's not a really good thing because you in subsurface you are not aware of the structure's boundaries that much. So if you just make a layer and then assume that's it, and then it just abruptly ends and there's a next layer, it's not the case.
Right.
Unless you have actual
Okay, so
drilling
it's
information.
L2 then. Yeah. Okay.
Yeah.
All right.
Thank you, Sina.
You're welcome.
Well, I think that's it. There are no other questions on YouTube, and neither here. So, Sina, I would like to thank you for the presentation.
Thank you very much for having me, and sorry about the technical problem at the beginning. For some reason, this wasn't working perfectly, and I'm glad that actually you emailed me because I would just assume that it's like an hour later.
Yes, there was some time mistake.
Yeah. Sorry about that. And thanks for having me. I hope you guys find ResIPy useful, and if there is any issues or problems or difficulties to work with, there is our GitLab page, my own email, a ResearchGate page, YouTube, and there's a lot of places you can just ask your questions, and we will be happy to help always.
Okay, thank you, Sina, and thank you everyone for watching.
Okay.
Bye-bye.
Thank you. Goodbye.